Let's focus on a body in white because it's a very common application, and there on a roof assembly. Key technologies which essentially enable this efficient concept design are, as a first thing, the definition of so-called stacked shell layers. So what you see on the bottom here is that, especially where you have like this flange area where different layers, which are different sheet metal parts in reality, meet, you see that essentially the design by itself is set up in a way that those flange areas are always just one single layer or one single surface, which makes then changes much easier, especially in areas where you have lots of layers meeting. Still, of course, when it comes to simulation, we want to have correct physical behavior. So our software takes care in the background and fully automatically of expanding those stackings into proper 3D layers with proper offsets, and also, as we see later on, proper connections. How is this working? Essentially, what you do, or what the user would do, is to say, we define a so-called stacking, and the stacking by itself is applied to the surface, and the surface by itself carries a definition on, okay, this is layer 2, 3, and 4 being situated here in this area. And as this is already, as we know, an area where things are connected, we already can go ahead and specify one or various connection types to those areas. A connection type would, for example, look like, okay, this is a point fastener. There is a spacing between those point fasteners of 40 millimeters. There is a longitudinal offset from the edge of 20 millimeters. There is even like a layout pattern if you have like various layers, if either all of these 3 or just a subset of those layers would be connected. But you already have quite some complexity you can define here, but it's all just rules which are applied automatically. So here is just an example right out of the software. You can see single layer definition. And if we switch the view mode, a multi-layer meshes with its connections. All of this is done really just by clicking the mesh button in the background automatically. It's really powerful. The next step is, of course, what about now parametric variability? Because this is what this is like one of our key pillars of efficient concept design. Luckily, 3D Experience relies on CATIA. CATIA, as you might know, has a very powerful parametric engine. I think it's still the best in the market. And essentially what you can do is you can set up those parameters. You can say, okay, let's change, for example, the B-pillar position. Let's change the widths of certain geometries, like those cross members, right? Let's change cross sections here. And once you do that, of course, you can go and utilize this concept geometry, being exactly those stacking, those single layer geometries. And you can see that vast changes like moving a B-pillar like that, along with cross members, is actually quite an easy thing to do and to achieve. And if you might have some background here in the audience in CAD design, doing this with, I would say, traditional methods within generative shape design of CATIA, for example, is really a challenge. And you would need to think about this before you actually do the design. With our concept engineering approach, this is not a precondition. So far, when it comes to parametric variability, the other thing which is also quite interesting is the fact that somebody can now define so-called modules. And those modules are nothing else than like containers for different sub-assemblies you would have within your, I would say, major assembly you want to investigate. You have, for example, an A-pillar, a P-pillar, and a C-pillar assembly. And maybe you also have like a roof module or assembly or sub-assembly. And you want to switch from baseline to sunroof very easily. And together with the parametric engine and the automated updates of connections as well as meshes, this enables topological variability in a very powerful way.